Hey there, welcome to your Explainer study session on numerical root methods. I'm thrilled to be your tutor today as we figure out exactly how to efficiently zero in on mathematical roots. If you're an engineering or math student trying to master numerical methods, you are absolutely in the right place. Grab your notes because we're going to break down these concepts step by step.
So, let's start with a really crucial question for anyone studying engineering or math. What happens when just guessing a root's location simply fails? How do we systematically and precisely track it down? In the real world, like say, calculating the exact mass needed for a bungee jumper to reach a specific velocity, we can't just eyeball a graph. We need reliable algorithms. We need methods that trap the root and completely squeeze in on it.
All right, let's quickly map out our tutoring whiteboard for today. We'll cover bracketing the root, the geometry of the guess, updating our guesses, comparing convergence, the curvature trap, and finally, your final study guide.
Section 1. Bracketing the root.
Now, you might already be familiar with the bisection method, right? It's the one that simply takes an interval and chops it perfectly in half. But false position, which is also known as linear interpolation, introduces a specific, slightly more complex formula. Instead of just blindly halving the interval, it calculates a new root estimate, xr, based on the actual trajectory of the function at your upper and lower bounds. It does this by evaluating the function at those outer limits and effectively weighing the guess closer to whichever bound is currently yielding a value nearer to zero.
Moving on to Section 2. Geometry of the guess.
This brilliantly illustrates the geometric difference between our two methods. Bisection is a reliable but honestly, brute force halving tool. It literally doesn't care what the function looks like, it just finds the midpoint. False position, on the other hand, acts as a really clever shortcut. Imagine plotting your lower bound xl and your upper bound xu right there on a curve. False position draws a straight secant line directly connecting those two function values. Where that straight line intersects the x-axis, boom! That is your new, improved root estimate. It mathematically assumes the curve is basically a straight line between your two guesses.
Section 3. Updating the guesses.
Listen, this is a massive takeaway for your notes. Both methods actually share the exact same updating algorithm. First, you compute your new root estimate, xr, using either the halving method or that false position formula we just discussed. Second, you evaluate the function at that new root. Then, and this is key, you replace the old bound that shares the exact same mathematical sign as your new function value. So if your new point yields a negative value, it replaces the old bound that also yielded a negative value. Doing this guarantees the true root where the function actually crosses zero stays permanently trapped between your two bounds.
Section 4. Comparing convergence and efficiency.
So in a standard scenario, false position is your dynamic secant-seeking tool. Because it actually factors in the shape of the function, it typically rapidly approaches the true root. Bisection, meanwhile, just kind of plods along, reliably but slowly chopping that interval in half over and over again. Under normal conditions, false position will act like a rocket, leaving the bisection method entirely in the dust and giving you a highly accurate answer in far fewer iterations.
But wait, let's look at Section 5, the curvature trap.
All right, picture this. You're sitting in your exam, and you're asked to find the root of the function x to the 10th power minus 1, and you're given the initial bounds of 0 and 1.3. Now, this is a function with extreme sweeping curvature. You might immediately think, oh, I'll use false position, it's way faster. Well, let's see what actually happens.
The crucial point reveals itself after just 5 iterations. Notice how our slow and steady bisection method has dropped its true error down to an excellent 1.6%. It's incredibly close to the true root. But look at false position. The supposedly faster method is hopelessly stuck with a massive true error of 59.2%. It literally has barely made a dent. So why did our clever shortcut fail so spectacularly?
The underlying reason for this failure is that extreme curvature actually violates the core premise of false position. Remember, false position is built on the assumption that if a function value is closer to 0, the true root must be closer to that bound. But extreme curvature creates this frustrating phenomenon called one-sidedness. Because the curve bulges so sharply, our straight secant line keeps hitting the x-axis prematurely. As we update our bounds, one bracket point stays permanently fixed. You end up drawing slightly different lines from the exact same anchor point over and over, effectively stalling out. Bisection, though, it doesn't care about curvature. It just happily cuts the error in half every single time.
Which brings us to Section 6, The final study guide.
When you're deciding which method to use, remember these key takeaways. Bisection actually wins out when you're dealing with significant function curvature, or if you ever notice false position exhibiting that dreaded one-sidedness where one bound just won't update. This proves a vital lesson for you future engineers and mathematicians. You can never, ever make blanket generalizations about efficiency. No single numerical method is perfect for every scenario. And honestly, here is my absolute best piece of advice as a tutor. No matter which method you use, always take your final root estimate and plug it back into the original equation. If the result isn't very close to 0, you need to keep iterating.
I'm going to leave you with this final, provocative thought to ponder as you continue to study. If both of these bracketing methods have their unique flaws, bisection being generally slow and false position being super vulnerable to that curvature trap, how might we mathematically modify the false position algorithm to forcefully break it free when it gets stuck on one side? Think about how you might alter the function values to force that stationary bound to shift. Definitely keep that in mind for your next advanced study session.